Okay, guys. So we've looked at the models of memory. We have looked at the social and psychological elements that impact how we encode, store, and retrieve memories. We've also looked at what happens biologically when the brain, I guess, sustains some trauma. Next, what we're going to do is we're going to be looking at neuroplasticity. And the changes in neurons. And so essentially what we're looking at is what is the biological basis of memory formation. Now, this is a little bridge, I suppose, or a link between learning and memory. So how do we learn something and then transform it into memory, I suppose? So this is our dot point, neuroplasticity, and changes to the connections. So we're talking about the synapse between the neurons, including long-term potentiation and long-term depression. Now, these two terms here are very, very important. With both of them, what I would like you to remember as I'm going through this PowerPoint is what are the definitions, what are the biological changes that are happening or that are occurring, and how does this affect memory, okay? Now, the effects, that's like your application. So looking at the definition, biological changes, and how that affects our memory formation or storage. So essentially, what does that look like in real life? So what is learning? What is memory? Learning involves the acquisition of knowledge, whereas memory is the expression of that knowledge, okay? So once we've learned something, we can tell that we've learned something by retrieving a memory. So information, if the information is not learned, then it can't be remembered, okay? So essentially what we're looking at here is we have an experience, like a dance lesson, learning occurs, we store the memory, and then we can retrieve it, okay? Now, how does that actually occur at a biological level? Well, this is what we're looking at when we look at long-term depression and long-term potentiation. Okay. Before we do that, let's go back and recap the information that we've already learned, okay? Now, obviously here we have a neuron and we need to know the key parts, okay? So I'm gonna flip through just the really, really key parts of this diagram. So number one, they are our dendrites, okay? And they're very important. Number two, we have the nucleus, or the soma. 3 is our cell body. 4, we have our myelin sheath. 5 is our axon, and 6 is our axon terminals, okay? Now we know that information is received at the dendrites, okay, in a chemical form, and it goes into the cell body / soma, and it's converted into an electrical message, okay? That's called an action potential. So if strong enough, the action potential will go all the way down the axon, down to the axon terminal, and that will stimulate the secretion of those neurotransmitters, okay? Now, let's have a closer look at the image on the right. Now, as we know, holistically, this is called a synapse. It consists of 3 parts. So the first part is the axon terminal on the presynaptic neuron. We have the synaptic gap, and we have the dendrite on the postsynaptic neuron, okay? Now, within our synapse, we can see that we have the vestibules, and we can see that they secrete the neurotransmitter. Now, that neurotransmitter is taken up by those receptor sites on the postsynaptic neuron. When I'm talking about long-term potentiation and long-term depression, or really how we're making memories, I'm actually really just talking about this synapse here. I'm not really interested in the rest of the neuron. I just want to know what's actually going on in terms of the biological change within the synapse. Okay, so neuroplasticity refers to the brain, sorry, neuroplasticity of the brain refers to the way it changes in response to stimulation from the environment, okay? Now, this neuroplasticity, I suppose, is necessary for learning to take place. The brain is really only capable of learning because of its flexibility in adjusting to changes in the environment, okay? So essentially what we're seeing here is experience associated with learning cause changes in the brain, okay? Now, when that actually occurs, when we're actually having enough experiences to cause changes within the brain, it's actually causing a change to the brain's structure and function. When we're looking at learning specifically, this is the one I want you to really refer to, that's synaptic plasticity, okay? So this refers to the ability of a synapse to change over time, okay? Now, again, what I want you to refer to when we're talking about learning is this idea of synaptic plasticity, okay? So we know that the neuron or the synapse is that basis of memory formation and storage. When memory occurs, it occurs in the form of what we call a memory trace. And you will have heard me talk about a memory trace before, okay? So essentially all I want you to know is that when we're experiencing things, it causes changes to the connections or the synapse, yeah? Now, when we have a strong enough experience or when we learn something, I suppose, efficiently enough, it means that we have both structural and functional changes, okay? The one that's really important for long-term memories is structural changes. And essentially what occurs is this thing called synaptogenesis, when neurons form new synapses or strengthen those existing ones. So how do we know this? We know this through a few different experiments, and you will have looked at a few of them when you were in 1-2. So you may have looked at Jodie, or you may have looked at the cats whose eyes are sewn closed to see how their visual cortex has reacted to the lack of input in terms of environmental stimuli. There was another guy called Rosenvig, and so what he did was he put rats in 3 types of cages. So he put rats in either an impoverished condition, so that's this one here, so it was just one rat, it was a pretty boring cage. He put rats in a standard condition, so a normal cage, a few rats, and he put rats finally in a enriched environment, so this cage here, so like lots of environmental stimuli, pretty cool cage, lots of rats to play with. They stayed in the cages for 80 days and then their brains were dissected. What Rosenvig found was that the more enriched environment the rats had, the heavier were their cerebral cortexes, okay? So they were thicker, they were heavier, and when he dissected this further and looked under the microscope, he found that they had bushier dendrites, more synapses, and so that was evidence of neurotransmitter activity. So that's how he kind of concluded this idea that the more enriched your environment is, i.e. the more learning experiences that you have, the more likely you are to have biological changes within your brain, and your brains are therefore heavier. Why? Because you've made more synapses, i.e. synaptogenesis. So you've already heard me talk about this idea that when we form a memory, there are both physical and chemical changes that occur at a synaptic level, okay? Now, collectively, what this forms is a memory trace, okay? What I want you to think about is the last time you learned like a physical skill, okay? So for your, I guess, conceptualization of this idea, I want you to think about a sporting activity, okay? So think about the last time you learned a skill. It might be you learned how to kick a football, okay? So think about the first time you ever did that thing, okay? Now, I would assume that you're pretty bad at it. But when you practice that skill over and over and over and over again, what you might have found was that you were better at that thing, okay? So when you practice kicking the football, you get better, you get more accurate, you're able to do things that you weren't able to do before. Why does this actually occur? It's because of this process called LTP, or long-term potentiation, okay? Now, just to note, VCA will allow you to say LTP. This is a word perfect definition, okay? I want you to learn it as is. So this is a long-lasting strengthening of synaptic connections of neurons, resulting in enhanced functioning of the neuron, okay? Essentially what that means is this. When you repeat the stimulation of the same neural pathway, okay, now essentially that same skill is a neural pathway, yes? This strengthens the likelihood of those neurons firing together again, okay? Essentially what we're saying is that when you practice a skill, it will stimulate the same neural pathway. What that leads to is structural and functional changes. And then when you do it enough and these structural and functional changes occur, it means that there is more efficient communication between the pre and postsynaptic neurons. What that looks like in practice is that you engage in the skill more easily, okay? So you kick a football more easily, you can spin on one leg more easily, you can recall information about psychology more easily and more effectively, okay? So what we're saying is that biological changes occur. This leads to enhanced communication within the neurons. And then what happens, or essentially at the same time what happens, is that you can engage in a task much more easily. Why? You've learned something. Now that process holistically is called long-term potentiation. How do we actually know that this thing called long-term potentiation actually occurs? We know through the work of a guy called Eric Kandel, and he studied anaplesia, which is a sea slug. It's actually a Californian sea slug. This is information, it's just an FYI, you don't actually need to know it for the exam. So what he did was he grabbed some aplesias and he chose the aplesias because they have the largest neurons in the world. You can actually see how they change with the naked eye. You don't need a microscope. So essentially what he did was he actually stimulated them with a glass rod and he watched the gills, okay? If we have a look at this image down here, we can see the glass rod and we can see that when it's poked with the glass rod, it actually withdraws its gills, okay, here. When Kandel poked the aplesia enough times with the glass rod, the aplesia learns that it wasn't a threat to the sea slug, and it actually left its gill unfurled. Now, simultaneously, what he was able to do was he was able to actually see the changes in the neurons when he dissected the aplesia after the experiment. And so he actually knew, oops, ignore those sirens. So what he was able to do was he was able to see how before and after this learning experience, these neurons had actually changed in a biological way. So I've talked a lot about long-term potentiation and the associated structural and functional changes, okay? So let's actually talk about what those are, okay? Now, the first thing I want to say is that functional changes are only changes within the secretion of neurotransmitter, okay? Now, when we observe functional changes, this means a short-term memory has occurred, okay? So first off, what happens is, it doesn't look like an S. So first off, what happens is you have a neural circuit, okay? Now, let's say that this is a neural circuit here, and this is, I don't know, I'm just going to use kicking a football, yay. Okay, so you first learn to kick your ball, all right, and so you're stimulating this this neural circuit over and over and over again. Okay, so the first thing that happens is because you are kicking the football over and over and over again, what actually happens is you have increased secretion of neurotransmitter, particularly glutamate, okay? So rather than like just a few bits of neurotransmitter or glutamate, being secreted, you have lots. Yay, so much glutamate, woo! Oh yeah, look at that glutamate, so much. Anyway, a lot of glutamate, okay? Now, the other thing that happens is there's also increased sensitivity of the receptor sites on the dendrite, okay? So what that actually means is because there's all this like glutamate running around, your receptor sites like, oh my God, we have to be more easily activated by these neurotransmitters. So essentially what we're saying here is that less neurotransmitter activates the postsynaptic neuron than it did before, okay? Now, think of your neural circuit like a highway, okay? Now, think back to when the M1 or the Monash had roadworks. Essentially, the reason why they did that was because there was so much traffic, it was actually really, really congested. So the government was like, okay, there are all these cars on the road, so now there is a need for us to actually make more lanes so the flow of the cars along the highway is better, okay? Essentially, this is quite similar. This is quite similar to your neural circuits, okay? So essentially your neuron's like, oh my God, there's all of this neurotransmitter. We need to make this process a lot more effective. Well, how do we do that? The first thing that happens is there are more dendritic spines. So your dendrites get bushier, and you can say that, bushier dendrites. It's a super fun thing to say. So we've got our dendrites here and they just get bushier. Yeah, look at those bushy dendrites. Sexy, I know. Bushy dendrites. Yay. Okay, I'm not very good at this pen, but let's go with it. Okay, cool. So our dendrites are bushier, right? Now, we know that on our dendrites we have receptor sites. So when we have bushier dendrites, it actually means that we have more receptor sites, okay? And that's also kind of why there's increased sensitivity of the receptor sites. There's more of them, it's increased sensitivity, so kind of things are moving along a lot faster, okay? The other thing that happens, which is kind of weird, is we have these things called filigree appendages. And they grow from the presynaptic neuron, okay? So, I mean, I'm not going to do a very good job of this, but they grow, right? So you have these little shoots coming from your knobs, right? And so essentially what's actually happening, and it doesn't actually look like this, but let's go with it. But essentially what's happening is we are forming more connections, right? So with all of this, what happens is the dendritic spines, they meet these filigree appendages. And then what actually occurs is that we have more synapses. I talked a lot about like these synapses and these biological changes, okay? So we've talked about kicking a ball. We kick the ball over and over and over and over again, okay? What that means is that our neurons are stronger, okay? Why? We have more dendrites. We have more filigree appendages. We have more receptor sites, as we can see here. We can see that our receptor sites are more efficient. We can see that there's way more neurotransmitter, okay? So what that actually means is that our neurons communicate much easier than they did before. This neuron here with those growths, they effectively communicate much, much easier than these ones here because they have these additional offshoots and things like that. Also like additional lanes in the M1. What does that look like in real life? Well, it means that you can kick your ball easier. We kick the ball easier. So when things become stronger, they communicate better, and that means you can do the task much more effectively or easier. Why? You have learnt it. That's what learning looks like. Okay, so we've talked a lot about learning, okay, and long-term potentiation. So long-term potentiation is the potential for learning, okay? What happens when we need to forget something or we actually do forget a skill? Like what then? What happens biologically? Well, that term is called long-term depression, okay? It's not depressing. It means that that the activity has been depressed, okay? So this is the long-lasting decrease in the strength of synaptic transmission, okay? Essentially what happens is let's say, for example, you've learned a skill, kicking a ball, okay? And you've not done that thing for a long time, okay? Now, I mean, that term, use it or lose it is really apt here, okay? Now, what's happening is, we haven't stimulated that neural circuit, okay? Or we have had prolonged low-level stimulation. I wouldn't worry too much about this. I would more talk about like the lack of stimulation, okay? So we haven't stimulated pre and postsynaptic neurons in that particular neural circuit, okay? And what actually happens is the postsynaptic neuron becomes less responsive, okay? And this means the synaptic connection is weaker. Again, what that means is that there's less effective communication, okay? Now, what we actually might see here is this thing called pruning, okay? And that actually means those those neural circuits, they become weaker. Why? Because there's less of them. So less bushy dendrites, less neurotransmitter, less receptive receptor sites, things like that, okay? Now the thing is like why would we want long-term depression? Like, do you actually want to lose your memories? And the answer is, of course you do. I mean, if things are traumatic or if things are irrelevant to your life and you don't need them in the long run, then you might actually want LTD to occur. Now the other thing is this. Consider a circumstance where you're learning to dance and you've learnt an incorrect dance move or you've learnt the wrong technique. What you would actually have to do is you would actually have to forget that incorrect technique through LTD and then use LTP to correct that movement, okay? So essentially you have to unlearn the mistake before you learn the mistake. And that's why LTD is really, really important. So how are these different and how are they similar? It's really important that you know the differences and the I suppose the similarities between LTP and LTD. Okay, so the purpose. So the LTP essentially is learning. Okay, and this allows us to strengthen useful, important memories. LTD. This allows us to prune or eliminate unwanted or unimportant memories. That's forgetting. Okay, so we have learning and we have forgetting. When it occurs. So LTP, when there is repeated activation of the same neural pathway. LTD occurs due to the lack of stimulation of the same neural pathway. So that means that for LTP, the neural pathway is stronger. LTD, the neural pathway is weaker. What does that look like in terms of communication? Well, there's enhanced communication between neurons for LTP. For LTP, there is decreased communications. In terms of our sensitivity, they're more sensitive. For LTP, for LTD, they are less sensitive, okay? Both of them are long lasting and both of them involve glutamate, okay? Before I leave you, I want to talk to you about a structure, okay? Now the structure is really the same thing that I kind of spoke to you about when I first looked at this dot point with you, okay? Now in every single LTP, LDT question, I want you to make sure you're doing three things for you, okay? I want you to define the thing, okay? So define LTD. I want you to talk about the biological changes. So you can say that synaptogenesis is occurring and therefore neurons communicate more effectively, or pruning has occurred and so therefore neurons are communicating less effectively. And then I want you to tell me like what the effect of that is. So I want the application. So when you're applying to the scenario, I want you to tell me if something has been learnt or if it's been forgotten. Okay, now that is a structure that you can use for any long-term potentiation and any long-term depression question.